Hi there, follow-on video from the capacitor leakage current. What we want to do in this video is to ascertain the impact of putting voltmeters or oscilloscopes into circuits, because they do alter the circuit, particularly if you're trying to measure very small currents. Okay, previous circuit here, we've got a charged circuit, 10 volt DC, 10 kilo ohm resistor. We're measuring with a voltmeter, this voltmeter here, the charge current through the capacitor. So if we charge the capacitor up, we have 19 millivolts across the 10k. The 19 millivolts indicates that the load that it sees here, is then 5 megohms. Now, if we're using this capacitor as a reference, it does have a 10 meg ohm resistor physically across the plates. So if this was 10 megs, and previously we had 10 millivolts, which corresponds to 1 microamp and 10 megohms. If we've now got double the voltage, we've now got double the current. If we've got double the current, we must have added another 10 megohm load in parallel, which is the probe of the oscilloscope, which is set to 10 megs. And the other way to ascertain it is if we do the RC discharge on the oscilloscope here, we can ascertain the time constant of our RC discharge, and that time constant, if we measure it off the oscilloscope, that time constant is 6 seconds. So if we've got 6 seconds divided by 1 microfarad, that would mean that our RL is in the region of 6 megohms, because with the time constant from discharging from 10 volts, dropping 63% to 3.7 volts down the Euler's curve, it's a natural curve because capacitance is a natural effect, then it drops 63% to 3.7 volts in approximately 6 seconds, which would indicate that the load resistance, 6 seconds, 1 microfarad, the load resistance is in the region of 6 megs, and that's because we've put the scope into the circuit. We've added another parallel path. So the other way to ascertain the impact of components on the circuit, if we switch this back on, if we now disconnect the oscilloscope, so that's out of the circuit, but we add in a voltmeter, we're now adding in a voltmeter. This voltmeter is reading 10 volts. Okay, so we're just putting it into the circuit. We've disconnected the capacitor. The capacitor's not in the circuit, but the voltmeter is. So the voltmeter is seen as a load, and we do have current flowing as indicated by this meter. Now we have current flowing of approximately, again, 10 millivolts reading, which again approximates to 1 microamp, which again would indicate that if we've got 1 microamp flowing, that would indicate that the resistance of this meter here, is in the region of 10 megohms. So it does have an impact on a circuit, particularly if you've got very small current flows. If we disconnect the voltmeter, we obviously have zero current flowing because we've disconnected the circuit. If we change from a digital multimeter to, say, for example, an analog voltmeter, so what we've now got is an analog voltmeter, and it won't even get up to 10 volts. So this is a load on the circuit now, and we're now reading 3.9. We're now reading 3.9 volts, which is extremely high, which matches up with the voltage across here of about 6 volts. So what we can say is in that current flow, what we can say is we have we've got 3.9 volts across 10k, which means that we've got 0.39 milliamp flowing. Now we can do the resistance. The voltage based on this, it's reading, I would say 6 volts. So if it reads 6 volts and the current flowing is 0.39 milliamps, then that would indicate 6 volts. 6 volts divided by 0.39 millis is indicating that it only has a resistance of approximately 15 kilo ohms. That would indicate that the resistance of an analog meter is substantially lower than the 10 megs from a digital meter. So that actually proves by experiment that if you put an analog meter in, it has a significant impact on the circuit simply because it doesn't have the input resistance of a digital multimeter. But the advantage of an analog meter is if you're looking at slowly changing values, you can see how it changes without the numerics jumping about, which is difficult to read on a digital meter. So this video is proven by experiment the impact of voltmeters on a circuit. Thank you.